Hello, Vangelis. Sorry.
Hello,
I've
Adrian.
been telling the story of ESPT, started in Santorini, I think it was 2005 or something like that. And I have been telling that the concept on the background of the society it was just by the common frame of the public healthcare system that we're using in Europe. We came together, a group of European scientists, in order to develop recommendations or guidelines or advice how to use better pharmacogenetics for the public healthcare systems. Professor Manolopoulos is a leading expert in cardiovascular pharmacogenetics worldwide. He has been involved actually in all the clopidogrel evaluations and strategy. He's an European expert in projects, and is somehow he has certain similarities with us because he grew up as a scientist in different countries around the world. Probably in Holland or Netherlands was one of the places when he stayed more time. But finally, he decided to go back to his hometown, which is Alexandroupolis, and the University of Thrace in Greece, which is quite similar why we came back, or I came back here in Extremadura in the southwest. But in this place, Professor Manolopoulos developed a department of pharmacogenomics that now is using even advice, not only in pharmacokinetics, but also in pharmacogenomics for all hospital and region. But besides, is involved in very many projects around the world and around Europe. Right now, he's in Egypt, developing a teaching strategy with the current next president of ESPT, which is Professor Daly. So, Vangelis, thank you very much for being here. I appreciate very much you as a human being, because your values, we share values in life and values in science, and I appreciate you most as a scientist as well. The floor is yours. Thanks a lot.
Thanks, Adrian. I will try to share my slides now, see how it works. Here you can see the hospital in Alexandroupolis, where I come from, and ESPT, of course, the European Society of Pharmacogenomics and Personalized Therapy. And I guess you're all familiar with the concept of pharmacogenomics. I have only this one slide. Well, the general idea is pharmacogenomics and pharmacogenetics deal with what our genome does to the drugs. So, and the traditional approach when prescribing medicines for centuries has been you give a dose, which is the indicated dose for the specific indication. And then, well, luck has it, some will respond, most will respond, hopefully, but some will not respond, and some will exhibit side effects, often not very serious ones, but sometimes really serious. And for centuries, there was nothing we could do about. But lately, the last 30, 40 years, of course, doctors have always been aiming at finding the right drug for every patient, taking into account any information they had about this personalization. Well, since the late 60s, early 70s, we started developing also tools to relate the genetic background with response to drugs. So we passed to the bottom part of this, the left side of my PowerPoint, where the idea is that if a specific genetic trait correlates with our response to drug, with a specific drug, then if we know in advance this genetic characteristic, for example, a metabolizing enzyme that is not functioning in a specific person because it does not have the gene, or the gene leads to a non-functional or dysfunctional enzyme, then we could in advance think or know that this person has a high chance of responding too much and exhibiting adverse drug reactions because he will accumulate the drug, and vice versa. If he expresses too much of this, the gene of the enzyme, he may have too much enzyme and then metabolize the drug too quickly before it gets a chance to function. So this idea is, if we have this information, we can proceed more costly and personalize a little more. And all this is not theoretical. It is based on observations that have been done at first with the enzyme, the metabolic enzyme CYP2D6, which is involved either exclusively or together with other metabolic enzymes in the metabolization of about 25% of the most common drugs we are using. And it has been established, and also Adrian has played a role when he was in Sweden in this correlation between CYP2D6 genotype and response to specific drugs, that we could, in principle, divide the human population into 4 large groups. One, which is the, I don't know if you can see my pointer, it's the yellow bar, the people who express the normal amount of enzyme, normally functional, and of course, this is always metabolizing. So there is a steady rhythm of metabolism going on when a drug appears. But then there are people who have one of the 2 DNAs, they have a dysfunctional, a polymorphism that leads to dysfunctional enzyme. The other one is normal. So those are called heterozygous, and they are expected to have reduced, diminished function of the enzyme. And then you have people who carry in both DNAs, carry in both the defective enzyme, and they probably have no ability at all. Of course, in these people, maybe a little of the drug may be metabolized by alternative routes, but in many cases, all the drug is accumulating there. And of course, there are people who, as we found out 2 years after the original discovery with the non-functional enzymes, that express too much enzyme, more copies of the gene of the enzyme, and they are metabolizing too fast, and they're called ultra-rapid metabolizers. And this idea has been more or less been found with other metabolizing enzymes, including CYP2C19, which is a central enzyme in our discussion today about clopidogrel. So for CYP2C19, we have the exact same bars with ultra-rapid metabolizers, normal metabolizers, intermediate metabolizers, and poor metabolizers. And we'll see how this affects response to clopidogrel. Now, before going to the specific examples, I would like to link pharmacogenetics with the broader concept of personalized medicine, which is the ability to offer the right drug, the right dosage to the right patient, for the right disease, of course, and at the right price, which is not, of course, a scientific issue, but often it relates a lot with whether a therapy will catch up in the end, be beneficial for the society. This personalization of medicine entails the integrated use of clinical and environmental and genetic and genomic and proteomic and other omic parameters. And omics, of course, is a big new page that we have opened in the personalization of medicine. Maybe if I have time, I will say just introduce the concept at the end of this lecture. And of course, we don't talk about personal medicine, so we don't claim that we will find a drug for every specific person. That would be preposterous, and probably people would think we're not serious if we talk about personal medicine. This could be perhaps is the holy grail. So at the end of the road, maybe 200 years later down the road, we may be able to really specify. But now we're talking about personalization. So mostly grouping people in categories. And a new term has been introduced. You may have heard of that. It's more and more catching up. It's called precision medicine. And responsible for this new term is mainly this guy. You may remember him, Barack Obama in the middle. Actually, on the left, you can see the current president, also who at the time, January 2000, was the vice president. And then he launched the term precision medicine together with a large sum of funding that the US government gave in order to essentially advance the pharmacogenetics for several diseases, cancer, as Obama mentioned, diabetes, but also a lot of other categories, including cardiovascular drugs. So the Americans have moved quite a lot. FDA has been constantly incorporating pharmacogenetic information in its site, and last year they released a list of evidence-based pharmacogenetic variants. And here I would like to make a distinction to clinicians from what told me. We're not talking about experimental stuff. Pharmacogenetics, of course, it's a huge field of research, and we're were participating in that, me, Adrian, and many other scientists. But now we're not talking about this, we're talking about application. We're talking about cases where the correlation between a gene and the response to a drug has been established at some level at the clinical level. So it's not just drug level, but clinical response correlation with a side effect or something. And even such pairs, they exist, several of those exist. And I'm not going to go into the whole list of FDA, it's 300 or 400 drug pairs, drug that are listed there. This is another way of showing how important pharmacogenetics in the clinic. In this case, taking the inserts of drugs that are prescribed in the USA, the inserts of the drug, and looking at the ones that have pharmacogenetic information. It's more than 400 that do have pharmacogenetic information on what topic they are. And you can see oncology is on top with about 30%. Those that are a little older, maybe 3 or 4 years older now, maybe oncology is a little more, but still on top. Psychiatry comes second. Historically, was the first field to find the correlation. And you will appreciate that cardiology is also 7-8%. So from all pharmacogenetic information, 8% refers to cardiovascular drugs, which is not. From the associations that have been established, therefore, I was invited to talk about 2 of them, about clopidogrel and about statins. I will, if I have time in the end, also mention just 2 slides about the beta blockers, which I also think it's also an interesting pharmacogenetic association, and it's useful for MedeA, you are testing that, but it might be useful. See, now clopidogrel to start with. Well, most of you probably are familiar with quite a lot. It's an antiplatelet agent used both to prevent ischemic events in atherosclerotic patients, both in STEMI and non-STEMI cases, and also, of course, prevention for thrombosis after stenting. Here we prescribe clopidogrel often together with aspirin. What's important to remember from the pharmacogenetic perspective is that clopidogrel is a prodrug. So we provide the inactive original drug, the clopidogrel, and this is transformed through metabolic enzymes to the active substance that really acts the job, works in the body. And something you probably all are familiar with is what we've been calling the resistance to clopidogrel, which has been well documented in the years since the 80s that we've been using clopidogrel. And it's a fact that about 30% of patients exhibit resistance. And the way we measure that is by looking at platelet aggregation, because this is what clopidogrel does. It reduces platelet aggregation, or their propensity to aggregate, and that way it protects from thrombotic events in the circulation. So when we measure platelet aggregation, this is in the population, this is what we get. We get about 70% or less that get inhibition, but there are people who do not respond in the middle, in this part you see it's 0 to 10. These are people who respond more or less to clopidogrel, but we also have an amount of people that not only they don't respond, they may even have a counter effect, which has not been explained, and it's a puzzling thing. So the message here is that 30% of the patients do not respond, and in the case of clopidogrel, this is important because the ones that do not respond, there's no indication. It's just people who are not protected. The prophylactic action of clopidogrel is not there, so they may end up getting a thrombotic event sooner than they could have had they been protected. And of course, this is one reason for many cardiologists it's difficult to incorporate ethics into their practice, because it's not something they see. You give the clopidogrel, patient goes okay. If 3 years later he gets an event, or 2 years later, it's difficult to correlate it with the resistance to clopidogrel, only if you measure and if you are aware of it. But the clinical problem remains. Now here, this of course is a very packed slide, and you're not supposed to read it. It's a pharmacogenetic history of clopidogrel starting from the late 90s, from 1998, when the first, well, actually 1998, clopidogrel was launched worldwide as Plavix, and then a little later, in the beginning, 2-3 years later, cytochrome C19 was established as one that correlates with the response to clopidogrel. And since then, very quickly, actually already in 2009, 2010, FDA has moved, adding more and more information about this, even a black box warning, and suggesting with various wordings as the time passes that clopidogrel should be tested before prescription. And this goes all the way to today, to this year, that we had the latest, the more recent developments in this kind of suggestions. This is, as we said, the association. CYP2C19 STAR1 is the physiological enzyme, the natural enzyme most of us carry, and then STAR2 and STAR3 are defective enzymes. So carriers of one or two of these defective alleles have reduced or no activity of the enzyme. And then there's also people who carry another allele, STAR17, correlates with increased function of the enzyme. So they are ultra metabolizers. What we would get in this case is the people who do not, who carry the non-functional alleles, do not produce active clopidogrel, so they're not protected. The people who have the ultra-rapid phenotype, especially the homozygous STAR17, are at higher risk of bleeding, which is, of course, what we want to avoid when we prescribe clopidogrel. And this is just from one of the first papers that showed the correlation between CYP2C19 genotype and ADP aggregation of platelets. And you see on the left, on the A panel, when you divide the population by the genotype, STAR1, 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 STAR2, they have similar aggregatory propensity. When after a week of dosing with clopidogrel, there is some clear reduction in most of the patients who carry the normal genotype. The ones who carry a dysfunctional allele, STAR2, in some people have responded to some extent, but in principle, they do not have the beneficial effect. And this, of course, has been taken further up in early studies in JAMA and New England Journal of Medicine, correlating the presence of this non-functional allele, STAR2 and STAR3, with cardiovascular death, myocardial infarction, ischemic stroke, and this is a summary. You see the red overall points to correlation with genotype. So there seems to be a relation. And there have been several meta-analyses of such and I don't have any more detailed slides here, but there have been also in recent years also prospective study, in the Taylor study in the Netherlands, that have shown also prospectively that genotyping for CYP2C19 in advance and using this information to adjust prescription or other antiaggregant is helpful and improves, reduces events like stroke and myocardial infarction. Now, perhaps you're familiar with CPIC, which is the Clinical Pharmacogenetics Implementation Consortium, is a consortium of scientists and clinicians that look at the pharmacogenetic information and produce guidelines, publish guidelines as to how this can be implemented in the clinic. The guideline on clopidogrel already, the first edition was in 2011, and even the most recent one, essentially passes the same message, and that is people who carry either one or two defective alleles should not be prescribed clopidogrel, but an alternative agent such as prasugrel or ticagrelor or clopidine. And this remains, this is how it is, and it has been proven. Now, if you ask me how much it has been taken up in hospitals, well, in some places it's been taken up, others lag behind. Here I have a good example from one major hospital in the USA, which is using that in the information system of the hospital. And then once the doctor prescribes Plavix and the genetic information on the patient is available, he may get up this pop-up screen telling to him that his patient is an intermediate metabolizer of clopidogrel. So, and suggesting him to follow an alternative route. So either prescribe prasugrel or prescribe ticagrelor, and of course, also this a little more information in which cases this would not be possible. And then a third option for the clinician is to continue with clopidogrel, but then it has to give a primary override reason. So why are you insisting to provide clopidogrel, although you know that he has this intermediate metabolizer phenotype and he may not get the protection? So that way, it has been shown that makes clinicians think twice, and this helps incorporate this pharmacogenetic information into the clinical practice, and that's what we need in every hospital if we want to advance. Going to statins, which is another, well, a very broadly used category of anti-lipidemic drugs. And there are several of them, at least 6 or 7: simvastatin, atorvastatin, pravastatin, lovastatin, rosuvastatin, pitavastatin, and maybe there's 1 or 2 more I'm missing. Mostly, at least in Greece, atorvastatin is the main used, but simvastatin also is a classic, and some of the other rosuvastatin and pitavastatin, newer ones, are also getting some part of the prescriptions. They're all inhibiting a critical enzyme in the synthesis of cholesterol. We know they're very effective in reducing LDL cholesterol and total cholesterol, not as effective with triglycerides, maybe to some extent 10–20% or in some patients, but often in patients with hypertriglyceridemia, you need to prescribe something additional for the triglycerides. They have pleiotropic effects, and it's clear, it's established that they reduce the heart events, coronary artery disease, and all events that follow from this indication. Now, mainly they're well-tolerated drugs. The main side effect or the most serious adverse drug reaction exhibited by statins is rhabdomyolysis. So it starts with muscle pain, injury, myopathy, and if statins continue, you may get rhabdomyolysis, and the patient may even die if he remains with the drug. And this has been always the main reason with statins until some indications have showed that there may be a pharmacogenetic correlation. That the first indication had to do with the enzyme CYP5, but that may or may not be true. What then emerged in 2008 with one of the first genome-wide association studies in pharmacogenomics, where you get patients that experienced rhabdomyolysis and patients that did not experience, with the same dose of simvastatin, high dose of simvastatin, comparing them at the genetic level and seeing what difference there is. And this is a beautiful result that emerged. People who in these two groups, they have one difference in one SNP, they had one polymorphism in one gene. And this is with this kind of studies, you can identify it, and you see it there on top very clearly. And this is a transporter, non-ion transporter, that is polymorphic, and it has been shown from this study, and then several others confirmed it, that people who carry the normal genotype, this TT genotype, have a risk, a very low risk, below 1%, to experience rhabdomyolysis with a high dose of statin. And people who have heterozygous for the allele, the C allele, they have a 3 times higher risk, and people who are homozygous, and this may be 1-2% of the population, they have 10-15 times higher. So they are really at a high risk of experiencing rhabdomyolysis. And then the Clinical Pharmacogenetics and Implementation Consortium used this information, started publishing guidelines on how to apply that. And essentially, to make a long story short, the idea was that people who carry the TT or 1 or 2 of the CC or 1 or 2 of the alleles, the dysfunctional alleles, should not be prescribed high doses of simvastatin, which was the one that has been mainly affected. Also, we know for other statins that this is also a point of concern, and we should avoid. And this association has been very well established with meta-analysis of patients. You see here again the correlation between this polymorphism T521C and jumping from 2010 to 2022. This is a very recent paper published in Clinical Pharmacogenomics, where in a study in a hospital that does apply this genetic information in advance. So the patients that are to be prescribed high dose of statin, they are genotyped, and then information goes back to the clinician. And the interesting thing about this study, which has to do with the clinical implementation, is that the information that went back to the clinician in 65% of the cases that he deals with about 1,700 patients, in 65% of the cases, the clinician did use the information to change and adjust the dose of the drug and found it useful. So that means that it's not only some information that is generated by a lab, but it's information that a clinician can use to adjust the dosing of statin accordingly. And in the hospital where this has been done, this is in Mount Sinai Hospital, there is also an information system, and there again, you get a screen when you prescribe a patient with instructions on how to proceed. This is a pop-up screen. There's several other pages. It's very useful and helpful for a clinician. And these are the newest version after 3 or 4 editions of the guidelines. They are now incorporating 2 more genes, the pig glycoprotein and 1 cytochrome, which are involved in specific statins. And these guidelines now are very complicated. So look how we adjust depending on the intensity and the gene that is non-functional, how we adjust for every specific statin, because the complication with statins is that each of them has a little different metabolism. So it's not a class thing. Each of them has to be addressed specifically. And in this case, there are specific guidelines you see for atorvastatin, lovastatin, pitavastatin, and then also not in relation only to the transporter, but also to the other enzymes. So this is now just to touch a little on the work we've done in my lab on pharmacogenetics, and we look to a different aspect, or what we discussed so far, the adverse drug reaction of statins. But for several years, several groups looked for whether this same polymorphisms do affect the response to statins. So difference in levels. We had several studies, 5 or 6 publications for all the different enzymes that have been at various times correlated in some studies with the efficacy of the drug. And we could not find any association. And more or less, this is the general agreement now that with genotyping and pharmacogenetics, you don't find any useful information for the effectiveness of statin. There you proceed with the other clinical indications you have and the other clinical information. But for the rhabdomyolysis and for the ADRs, they can be very helpful. One word for the beta blockers, which of course everybody is familiar with. I clarify that beta blockers are an easy drug. You can give it. It is metabolized. Many of them are metabolized at C2D6, which is polymorphic. So when you prescribe the same dose to several different patients, the levels of the drug in their blood may be quite different, may differ 3 or 4-fold. But beta blockers having a very broad therapeutic window, this is not a problem, except in one case. And this is what I want to tell you about. This is the case of metoprolol, which is one of the best established beta blockers used in several indications and also in heart failure. Now, in heart failure, we need to dose metoprolol a little more carefully. So we need low dose. We don't need very high levels in the blood. And in that case, it would be very useful to adjust for the pharmacogenetic background patient. And already some bodies like the Dutch Pharmacogenetics Working Group, which is in the Netherlands, but produces guidelines in a similar way like CPIC, which is in the United States, and it's pretty well respected, has already published guidelines correlating metoprolol with C2D6 genotype. And the idea is that in patients that are poor metabolizers, they have 2 inactive alleles, the starting dose for metoprolol when the indication is heart failure should be reduced to 25%. If it has 1 decreased allele activity, then it should be reduced to 50%. So, conclude some thoughts of mine. Is cardiovascular drug pharmacogenomics and therapy personalization a reality or a hype? And I think many clinicians have this question in their mind. Well, from the perspective of a researcher, of course, like me and Adrian, is of course a reality. For you, busy or, well, allow me to say, perhaps not very well educated in genetics clinicians, maybe this is too much of a hype. I think the reality is that it's an uphill long distance track. We must strive to continue successfully for the benefit of our patients and society. So we have to implement the information we have available and advance further, improve, and then even also these biomarkers, because you could call any pharmacogenetic genotype information as a genetic biomarker, improves us and brings us one step closer to materializing personalized medicine. And in my opinion, the goal of personalized medicine can only be achieved when all stakeholders in the field work together with a willingness to accept occasional paradigm change in their current approach. So some of you have to take the lead, implement pharmacogenetics, show the use of it to the patients, to the rest of the doctors, and someday, well, this will be further incorporated. And I think efforts like what Adrian and all of you are doing with MedeA in Spain are really exactly what we need to advance the field further. So, well, of course, one should think that it's only genetics. I said that before, but there's many factors that interfere and affect the response to a drug. That's why if you use a pharmacogenetic information and you don't get a difference like you expect, don't get disappointed. It's not the only thing that affects the final end result of the drug. Several things that may have an effect. How we perceive the future, this is, for us, it's only the first step, and for all of us. This is only the information from the genome you get on the very left here on top. But then now, at the research level, epigenetic studies, proteomics, metabolomics are also studied. We're looking for biomarkers also at that level for every specific drug and effect. And as information comes up, it's incorporated together with all the clinical history, family history, all other information related to the patient, to the electronic health record, and the treatment decision comes. So of course, all this information is much more than a clinician can handle. That's why IT solutions help them, but I have to also make a clear statement that this does not replace the clinician whatsoever. The more information we have, the more we need doctors who can apply it. And no matter how much information we get at the biomarker level, at any of these levels, still the assessment of the clinician, of their patients, using all the tools, not only these, of assessing a patient will be indispensable and will be necessary in order to get not only the clinicians, neither the researchers, also the pharmacists have a role in implementing pharmacogenomics, the regulators who put the money, or the providers, the government who makes the decisions and issues the laws and facilitates or inhibits these developments. And of course, patients are very much involved, and I think they have a positive forward, and the industry who needs to adjust. Perhaps all these different buzzwords you hear all the time, they make a little more sense now. And this is a slide from Antoine de Saint-Exupéry. It's in Greek on the top, but in English the translation would be, as for the future, our task is not to foresee, but to enable it. So let's allow pharmacogenomics to happen. Let's be part of this revolution. Gracias.
Thank you very much, Vangelis. Kalimera. So thank you so much, Vangelis. I don't know if somebody here in the room, there's a selected stakeholders. Is the general director of the healthcare service, plus the main responsible of primary care, plus and the general managers of healthcare, meeting together with the leading primary care doctors involved in MedeA project, plus the research group. Today we will discuss about the next steps since we achieve the population that we plan. We have already 1,000 subjects involved in primary care. Si alguno de vosotros en la sala queréis hacer algún comentario, queréis hacer alguna pregunta, si no.
Adrian, if I may make a comment myself on the conversation, as I have the chance to be here with you and these other people involved, I should tell you that Europe is looking very carefully at your project in a good sense, that, and with a lot of hope, because it's the kind of projects that can influence what happens in all Europe, like the PREPARE study that has been completed in the European study you're familiar with, but your study is even more implemented, is even more real-world pharmacogenetic implementation. It may have an even more big effect on what the average country does, or the average area in all Europe with the personalized medicine and pharmacogenetics. So really, I really hope it will be successful, and it will set an example for all Europe.
Thank you so much for your work, Vangelis. You know very well, and thanks for your advice all the time. We're planning a meeting of all the experts that will take advice probably mid-December, personally here. I hope you can come. Thank you. Is there any question in the room? No. Well, Kalimera, Vangelis, good luck in Egypt. Take care. Warm regards and see you then. Thank you.